Imagine you want to find something. Not search for it in the way you search for keys, but locate it precisely. Pin down exactly where it is and exactly how fast it is moving. Simple enough request. We do this with objects all the time. A radar pulse bounces off a plane and tells you its position and its speed in the same breath. No conflict, no cost. Now make the object smaller, much smaller. Keep going until you're no longer talking about things you could hold or see, or even meaningfully picture. At that scale, something changes. And it does not change because our instruments get clumsier. It changes because the act of finding something, the physical act of reaching out and touching it with light, with any signal at all, is no longer neutral. It is no longer just looking. It is participating. For a long time, physicists assumed this was a temporary embarrassment, a problem of scale and sensitivity, that somewhere ahead of us was a more refined method, a gentler probe, an instrument precise enough to find a particle without leaving a mark. The uncertainty felt like a gap in our capability, something engineering would eventually close, but the mathematics said otherwise. And when the mathematics and the intuition disagreed, it was not the mathematics that eventually gave way. What gave way was the picture underneath the question, the quiet assumption that the particle was already somewhere, already moving at some definite speed, just waiting to be found without disturbance. What if it was not waiting at all? What if definite position and definite momentum were never both sitting there, fully formed, before anything measured them? That is not a philosophical provocation. That is where the physics points. And it points there not by accident, but by necessity. If you like exploring questions like these, feel free to leave a like and subscribe. And if there is a question about the universe you find yourself wondering about, let me know in the comments. We might explore it next. With that said, let's get back to the topic. The question is not whether we are measuring reality wrong. The question is whether the reality we assumed was there, crisp, located, fully formed, was ever the right picture to begin with. There is an explanation that feels so reasonable it becomes difficult to move past. It goes like this. When you measure something very small, you have to hit it with something. A photon, a pulse of energy, some kind of signal that bounces back and tells you where the particle is. And when that signal hits, it disturbs the particle. It nudges it, changes its speed slightly. So of course you cannot know both position and momentum at the same time. By the time you have found where it is, you have already altered how it was moving. The measurement ruins the information. This explanation is clean. It is intuitive. It maps onto things we already understand. And it is almost right in the way that makes it dangerous, because it points in the right direction while stopping just short of the actual destination. It lets the listener feel like they have understood something when the deeper thing has not yet been touched. The disturbance explanation assumes something very specific. It assumes the particle had a definite momentum before you measured its position, that there was a real, exact value sitting there, and your clumsy photon came along and scrambled it. The uncertainty in this picture is damage. Something that existed was knocked out of place. If only you could measure position without transferring any momentum, without touching the particle at all, you would have both values intact. The limitation is in the method. The information was always there. Physicists took this seriously. It is a reasonable thing to take seriously. If the uncertainty is just disturbance, then it is an engineering problem. A hard one, perhaps an impossibly hard one given our current tools, but a problem of the same kind as other problems we have solved by being more careful. You design a gentler experiment. You find a way to locate the particle without kicking it. You close the gap. But here is where the picture quietly falls apart. Because when you follow that reasoning all the way through, when you actually try to design the gentler experiment, not just imagine it, but work out its mathematics, you find that the uncertainty does not shrink. Every attempt to reduce the disturbance on one measurement increases the uncertainty in the other, not because the instrument is still too rough, because the attempt to be precise in one direction mathematically widens the gap in the other. The two quantities resist joint precision not because of what the tool does to the particle, but because of what precision itself demands at that scale. Werner Heisenberg saw this first, and he initially framed it in terms of disturbance. A gamma-ray microscope, he said, use a high-energy photon to pin down position precisely, and the recoil scrambles the momentum. The image made sense, but it was Niels Bohr who pushed back, quietly and persistently, and showed that the disturbance picture was not quite the foundation. It was a symptom of something deeper. The uncertainty was not produced by the measurement, it was revealed by it. And there is a difference between those two things that changes everything that follows. If the measurement produces the uncertainty, then a better measurement could reduce it. If the measurement reveals it, then the uncertainty belongs to the particle regardless of what we do. It is not a wound the instrument inflicts. It is a structural feature of what the particle is. And to understand why that is the case, why the mathematics insists on it, why no cleverness of design can root around it, you have to go one layer deeper. You have to ask what kind of thing a particle actually is, not what it looks like in a diagram, not the small sphere we instinctively picture, but what the physics actually describes when it describes a particle at all. And that description does not begin with a dot in space. It begins with something that oscillates. Something is moving through water. You are not watching an object cross from one side to the other. You are watching a shape travel, a rise and a fall, a pattern that moves through the water, while the water itself mostly stays where it is. If you put a small cork on the surface, it bobs up and down as the wave passes. It does not travel with the wave. The wave is not carrying water forward. It is carrying something else, a disturbance, a rhythmic change in the state of the medium that propagates outward from wherever it began. This distinction matters more than it first appears. A thrown stone carries its mass with it. A wave carries no mass anywhere. What it carries is a pattern, a relationship between parts of the medium that shifts position over time. The thing that moves and the thing that is moving are not the same thing, and when the wave passes, the medium returns to what it was. Nothing was transported, only the pattern travelled. Now think about what gives a wave its character. Two things define it most cleanly: its wavelength, the physical distance between one peak and the next, and its frequency, how many of those peaks pass a given point in a given time. These two properties are not decorative. They are what the wave is. Change the wavelength and you have a different wave. Change the frequency and you have a different wave. A wave without a wavelength is not a vague wave or an uncertain wave. It is not a wave at all. And here is the thing that carries weight for everything that follows. A perfect wave, a pure, single frequency wave, extends forever in both directions. It has no beginning and no end. It is not located anywhere in particular because it exists everywhere along its direction of travel equally. If you wanted to ask where this wave is, the answer would have to be everywhere it reaches, which for a perfect wave is everywhere. A pure wave is the most precisely defined thing in terms of its frequency, and the least defined thing in terms of its location. Those two facts are not in tension by accident. They are the same fact stated twice from different angles. What you get in practice, when a wave appears to be localized, when it seems to exist in a particular region of space rather than spreading infinitely, is not a pure wave at all. It is a collection of waves, many different frequencies, many different wavelengths, layered on top of one another in such a way that they add together in one region and cancel each other out everywhere else. The peaks and troughs of all those overlapping waves align briefly in one place, and that alignment is what you see as the localized disturbance. The wave packet, as it is called, is not a single wave. It is a collaboration of many, and the collaboration has a cost. To make a wave packet narrow, to squeeze the disturbance into a smaller and smaller region of space, you need more frequencies involved, more wavelengths contributing, more variety in the underlying components. The narrower the packet, the broader the range of frequencies required to build it. This is not a limitation of the materials. It is a mathematical fact about how waves combine. You cannot have a wave that is tightly localized and simultaneously composed of a single pure frequency. The two properties pull against each other at the level of the mathematics itself. Narrow in space means broad in frequency. That trade-off is baked into the nature of waves before any physics enters the picture at all. This would be an interesting geometric curiosity and nothing more, if it were only about water or sound or light. But it does not stay there, because the thing we call a particle, at the scale where the uncertainty principle lives, is not a small, hard object moving through space. It is described by something that behaves in every measurable way like a wave, and once that is true, everything the wave trade-off implies comes with it. In 1924, a French physics student named Louis de Broglie put forward an idea that had no experimental confirmation at the time and no real right to work. He suggested that if light, which everyone had assumed was a wave, turned out to behave like a particle under certain conditions, then perhaps the reverse was also true. Perhaps particles, electrons, protons, things with mass, things you could in principle hold a single one of, behaved like waves under certain conditions as well. He was not speaking loosely. He wrote down a precise relationship. The wavelength of a particle, he said, is equal to a constant divided by its momentum. The faster and heavier the particle, the shorter its wavelength. The slower and lighter, the longer. This was not a metaphor. It was a testable claim, and within a few years it was tested. Electrons were fired at a crystal lattice, a regular repeating structure of atoms, and on the other side they produced the same interference pattern that light produces when passed through a narrow gap. Bands of intensity and shadow, peaks and troughs, the unmistakable signature of waves overlapping and combining. Electrons, things with mass, things we had always pictured as tiny spheres, were diffracting. They were behaving as though they had a wavelength, because they did. This result has never gone away. It has been confirmed in more refined forms, with heavier and heavier particles, with molecules containing dozens of atoms, with objects large enough that the intuition strains to accommodate them. The wave behavior is not a quirk of electrons specifically. It is a feature of matter at the quantum scale. Every particle has a wavelength. Every particle, when not being forced into a definite position by an interaction, spreads through space the way a wave spreads. Not because it is literally vibrating in some medium we cannot see, but because the mathematical object that describes its state, the thing that tells you everything physics can tell you about it, evolves and propagates according to a wave equation. That mathematical object is the wave function, and it is worth being precise about what it is and what it is not, because the temptation is to think of it as a map of ignorance. a probability cloud that reflects our uncertainty about where the particle really is, as though the particle is somewhere definite and the wave function is just our best guess, smeared out because we lack the information to be more specific. That interpretation feels safe. It keeps the particle as a located thing and puts the uncertainty in us rather than in the world. But the wave function is not a map of ignorance. It is not a summary of what we do not know. It is the most complete description that physics can provide, not because our tools are limited, but because the particle does not have a more definite state than the wave function describes. The spread is not in our knowledge. The spread is in the particle. It occupies a range of positions not because we have failed to find the right one, but because occupying a range of positions is what particles do when nothing is forcing them to be somewhere specific. And here is where the wave trade-off becomes something more than a mathematical curiosity. Because if the particle is genuinely described by a wave, if the wave function is not a placeholder for hidden information but the actual physical state of the thing, then everything that is true of waves is true of it, including the trade-off, including the fact that a wave localized in space cannot simultaneously be a wave of pure single frequency. And in the language of matter waves, frequency and wavelength are not abstract properties. They are directly connected to the physical quantities we care most about: position and momentum. Place yourself beside a stretch of open water on a calm day. A single wave passes, long, slow, even. It rolls across the entire surface in front of you, crest to trough, repeating in a steady rhythm as far in either direction as you can see. If someone asked you where that wave is, you would pause. The question would feel slightly wrong. The wave is not somewhere. It is everywhere it reaches. It fills the space available to it. Asking for its location is like asking for the location of an afternoon. The concept does not quite fit the thing. Now imagine a very different situation. A boat has passed in the distance, and a single concentrated ripple moves toward you. A short burst of disturbance, a few crests bunched together, travelling as a group across otherwise flat water. This one you can point to. It is there, moving left to right, occupying a definable stretch of the surface. You can watch it pass a fixed point and say, "It arrived, it was here, it has gone." Location feels like the right concept now. The disturbance has a place. These two situations are not just visually different, they are mathematically different in a way that reaches much deeper than appearance. The first wave, the long, even, endless one, is as close as nature gets to a pure wave, a single frequency, a single wavelength, repeating without variation. It is the simplest wave there is, and its simplicity is precisely what makes location impossible to assign to it. To be pure in frequency is to be spread across all of space. Purity and locality are opposites at the level of what waves are. The second wave, the compact ripple, the one you can point to, is not pure at all. It is a mixture. Many frequencies, many wavelengths, each contributing a little, their individual crests and troughs aligning in one region and working against each other everywhere else. The localization is produced by the interference, by the cancellation, by the fact that outside the packet, all those component waves have fallen out of phase with each other and summed to nothing. The location of the packet is real, but it comes at the price of frequency purity. You cannot have both. For a particle described by a wave function, position works exactly this way. When the wave function is spread broadly across space, when the particle has no strong tendency to be found in one place over another, the wave function is close to pure, close to a single frequency, smooth and extended and coherent across a wide region. Ask where the particle is in this state, and the answer is genuinely open. It could be found almost anywhere along that spread. There is no hidden answer. The spread is the answer. When the wave function is narrow, when repeated measurement would reliably find the particle in a small region of space, the wave function is a packet, compressed, localized, built from many frequencies layered together in just the right proportions to cancel everywhere except that small region. The particle is findable. Location has become a meaningful concept for it. But the cost of that compression is already embedded in the structure of the wave function itself before any second measurement is even attempted. The packet is narrow in space, and a narrow packet, by the mathematics of how waves are built, is necessarily broad in something else. That something else is frequency. And for a matter wave, frequency is not an abstract property of the oscillation. It is directly and precisely connected to momentum. The relationship de Broglie wrote down makes it exact. Higher frequency means higher momentum. Lower frequency means lower momentum. A wave function built from many frequencies is therefore a wave function that does not have a single momentum. It has a range of momenta spread across whatever band of frequencies was required to build the localized packet. The narrower the position, the wider that band must be, and the wider the spread in momentum that comes with it. This is not yet the uncertainty principle. It is the wave geometry that makes the uncertainty principle inevitable. Take the wave packet and compress it, not gently, deliberately, forcefully, as a thought experiment with no practical constraints. You want the particle to be found in a smaller and smaller region of space. You want position to become more and more precise. So you narrow the packet, you squeeze it, you pull its edges inward until the region it occupies is a fraction of what it was. Watch what happens to the wave function as you do this. The packet was already a mixture of frequencies. That was how it was localized in the first place. But as you narrow it further, the mixture has to change. The cancellation that makes the wave function vanish outside the packet has to become more aggressive. It has to eliminate more of space, more thoroughly, leaving a smaller and smaller region where the wave function survives. To do that, the range of frequencies contributing to the mixture has to widen. More frequencies must be recruited. The spread in the underlying components must grow to accomplish the more aggressive cancellation. This is not an engineering limitation. You're not running into the boundaries of what current technology can manage. You are running into a mathematical constraint that exists prior to any technology at all. It is a property of Fourier analysis, the branch of mathematics that describes how any shape, any wave pattern, any localized disturbance can be decomposed into pure frequency components. Fourier analysis says, with complete generality, that the more compact a wave packet is in space, the broader its frequency spectrum must be. The relationship is precise and reciprocal. Halve the width of the packet, and you must at minimum double the range of frequencies required to construct it. There is no exemption. There is no workaround. The mathematics does not have a loophole. Now carry this into the physics of matter waves. The wave function of a particle is a wave packet. Its spread in space corresponds directly to the uncertainty in the particle's position, the range of locations where the particle might be found if you checked. Its spread in frequency corresponds directly, through de Broglie's relationship, to the uncertainty in the particle's momentum. These are not loose analogies. The connection is exact. Momentum is proportional to frequency for a matter wave, so a broad frequency spectrum means a broad momentum spectrum, and a narrow frequency spectrum means a narrow momentum spectrum. And Fourier analysis has already told us what is possible. A narrow packet, precise position, requires a broad frequency spectrum, imprecise momentum. A narrow frequency spectrum, precise momentum, requires a broad packet, imprecise position. The two cannot both be narrow simultaneously. The mathematics forbids it, not as a practical matter, but as a structural one. You are not choosing between two measurement strategies. You are navigating a constraint that is built into the wave nature of the particle before any measurement takes place. Heisenberg's uncertainty principle is the physical statement of this mathematical fact. The product of the uncertainty in position and the uncertainty in momentum can never be smaller than a fixed minimum value, a value set by Planck's constant, the fundamental quantum of action that appears wherever the classical world gives way to the quantum one. This minimum is extraordinarily small by everyday standards, which is why the constraint is invisible for objects of ordinary size. A thrown ball has a wavelength so vanishingly short that the corresponding uncertainty in its position is far below anything detectable or meaningful. The constraint is there, operating faithfully, but buried so far beneath the scale of classical objects that it produces no observable consequence. At the scale of electrons and photons and the fundamental constituents of matter, it produces every observable consequence. The uncertainty is not a rounding error at that scale. It is the dominant feature. It shapes the size of atoms, the stability of matter, the behavior of everything that quantum mechanics describes. And it does all of this not because measurement disturbs, but because the particle, as a wave, could never have had both properties precisely defined at the same time. The localization cost is not paid at the moment of measurement. It was always there, waiting in the structure of the wave function itself. Momentum is not speed. This is worth sitting with for a moment before moving forward, because the instinct is to treat them as the same thing, or close enough that the difference does not matter. Speed is how fast something moves. Momentum is how much motion it carries, which depends on both speed and mass together. A slow-moving truck and a fast-moving tennis ball can have the same momentum if the numbers work out. But even setting mass aside, even in cases where mass is fixed and momentum and speed move together, there is something about momentum at the quantum scale that makes it fundamentally different from the everyday picture of a thing moving quickly or slowly through space. In classical physics, momentum is a property of a trajectory. Something has momentum because it is going somewhere, at some speed, along some path. The momentum belongs to the motion, and motion, in the classical picture, is something an object does continuously. It occupies one position, then a nearby position, then a nearby position after that, tracing a smooth, unbroken line through space and time. Momentum is what you read off that line. It is the slope of the trajectory at any given moment. At the quantum scale, there is no trajectory in that sense. The particle does not move from one definite position to the next along a smooth path, because it does not occupy definite positions between measurements. The wave function evolves, spreads, interferes with itself, and when a measurement is made, the particle is found somewhere. But the path it took to get there is not a well-defined concept in the way classical physics assumes. So momentum cannot be the slope of a trajectory, because there is no trajectory to take a slope of. What momentum is, for a quantum particle, is something that belongs to the wave itself. Specifically, it belongs to the frequency of the wave. A matter wave oscillating at a single pure frequency has a single definite momentum. That is the quantum mechanical definition, and it is exact. The frequency of the wave function determines the momentum of the particle. Higher frequency, higher momentum. Lower frequency, lower momentum. The two are proportional, connected by Planck's constant, and the relationship admits no ambiguity. This means that a particle with a perfectly definite momentum is a particle whose wave function oscillates at a single pure frequency. And you already know what that wave function looks like. It is the endless, extended, infinitely spread wave, the one that fills all of space, the one you cannot point to, the one for which location is not a meaningful concept. A particle with exact momentum is a particle with no position at all. It is everywhere its wave function reaches, which is everywhere. And a particle with a reasonably well-defined momentum, not perfectly precise but close, has a wave function that is dominated by a narrow band of frequencies, close to pure but not quite, extended broadly across space but not infinitely. Its position is deeply uncertain, spread across a large region, because the near purity of its frequency spectrum means its wave function has not been built from enough components to cancel itself out anywhere. It lingers everywhere it reaches, with no strong preference for any particular location. Now compress the momentum uncertainty. Narrow the band of frequencies. Move toward a purer wave function, a more precise momentum. Watch what happens to the spatial spread. It grows. The wave function extends further. Position becomes less defined as momentum becomes more defined, because the narrowing frequency spectrum means less cancellation, means a broader spatial envelope, means the particle could be found across a wider and wider range of locations if you checked. The trade-off does not pause or relent. It operates continuously and reciprocally in both directions at every point along the spectrum between perfect position knowledge and perfect momentum knowledge. What sits at either extreme is not a practical impossibility, but a mathematical one. Perfect momentum means a single frequency, means infinite spatial spread, means no position at all. Perfect position means infinite frequency spread, means no single momentum at all. In between those extremes lies every real quantum state, every actual particle in every actual physical situation, navigating the constraint, never escaping it, always carrying some irreducible combination of positional spread and momentum spread, whose product cannot fall below the minimum Planck sets. The constraint is not imposed from outside. It is not a rule added on top of the physics. It emerges from what momentum is for a wave and what position is for a wave, and the mathematical relationship between the two that was already there before any physicist wrote it down. Take an electron near a nucleus. The electromagnetic attraction pulls it inward continuously. Nothing in that force prevents the electron from falling all the way to the center and staying there. In a classical picture, that is exactly what should happen. The electron should spiral inward, radiating energy as it goes, and come to rest inside the nucleus. Matter should collapse. It should have collapsed long ago. It does not. As the electron is drawn closer to the nucleus, its position becomes more confined, squeezed into a smaller region of space. A more confined wave function is a narrower packet, and a narrower packet must be built from a broader range of frequencies. A broader range of frequencies means a broader range of momenta present simultaneously, and a broader range of momenta means higher average kinetic energy. Confinement costs energy. The tighter the confinement, the higher that cost. So two things compete. The electromagnetic attraction pulls inward, lowering potential energy as the electron approaches the nucleus. The wave nature of the electron resists that confinement, raising kinetic energy as the position spread narrows. At some distance from the nucleus, these two effects reach equilibrium. The energy saved by moving closer is exactly offset by the energy cost of the increased momentum spread. The electron settles there, not because something holds it in place, but because moving closer would cost more than it saves. That settling point is the ground state of the atom. Its size is not arbitrary. It is not a coincidence of the particular charges involved or the particular mass of the electron. It is set by Planck's constant, the same number that appears in the uncertainty relation, the same floor that the product of position and momentum spread cannot fall below. The scale of the atom is the uncertainty principle made physical, made visible, made into the architecture of matter itself. Remove the principle and atoms collapse. Restore it, and they settle into the sizes we observe, confirmed to extraordinary precision across a century of experiment. This is not the principle operating as a limitation on knowledge. It is the principle operating as a structural feature of what matter is allowed to do. The electron does not sit at the ground state because we cannot measure it more precisely. It sits there because that is the only state the physics permits, and this makes something fully explicit that the wave geometry only implied. The uncertainty principle is not a statement about measurement, it is a statement about which physical states exist. States of simultaneously sharp position and momentum are not difficult to prepare. They are not waiting for better instruments to reveal them. They are absent from the set of states a particle can occupy, the same way certain geometric shapes are absent from Euclidean space. The mathematics does not contain them. Physical reality does not contain them, which opens the hardest question yet reached. If those states do not exist in the wave function, if the definiteness we assumed was always there is simply not present, perhaps it exists somewhere beneath the wave function. Perhaps the wave function is a surface, accurate and useful, but sitting on top of a deeper layer of reality that is fully determined, fully exact, and simply not yet visible to us. There is a response to everything established so far that feels like solid ground. The wave function gives correct predictions. It tells you the probability of finding the particle here rather than there, and those probabilities match experiment with extraordinary precision. But correct predictions do not guarantee a complete description. A map can be accurate without showing every road. Perhaps the wave function is the same, useful, reliable, but sitting on top of something deeper that it does not capture. The idea is called the hidden variable interpretation. Beneath the probabilistic description that quantum mechanics provides, there are additional variables, hidden ones, not yet accessible to theory or experiment, that specify the complete state of the particle. Position and momentum both have definite values at all times. The wave function does not capture those values because it is an incomplete description. A more complete theory would restore what the wave function obscures. The particle always knew where it was going. The uncertainty was always ours, not nature's. This was Einstein's position. He spent the later decades of his life convinced that quantum mechanics, for all its predictive power, had not yet found its foundations. A theory that assigns probabilities rather than certainties felt to him like a theory still waiting to be finished. The randomness was not real. It was a symptom of missing information. God, he said, does not play dice. The hidden variables were where the determinism he believed in was waiting to be recovered. And the position is not unreasonable on its face. Probability distributions appear throughout classical physics without anyone concluding that the underlying reality is genuinely indeterminate. The temperature of a gas is a statistical quantity, an average over the motions of an enormous number of molecules, each of which has a perfectly definite position and velocity at every moment. The statistics are in the description, not in the gas. The molecules are still there, still exact, still moving along determined paths. Why could quantum mechanics not be the same kind of thing? A statistical summary of a deeper layer that is fully real and fully determined, just not yet reachable. For decades, this remained an open question that no experiment could touch. You could believe the wave function was complete, that quantum probabilities were irreducible features of reality, or you could believe it was a placeholder for something deeper. Both positions predicted exactly the same experimental outcomes. The disagreement lived entirely in interpretation, and interpretation, unlike physics, does not submit easily to measurement. Then in 1964, a physicist named John Bell found a way to make it submit. He showed that hidden variable theories, if they are to be coherent, are mathematically committed to specific predictions about how pairs of particles correlate when measured independently. And those predictions are different from what quantum mechanics predicts. Not wildly different, not different in every case, but different enough that a careful experiment could reach into the philosophical disagreement and extract a physical answer. The question of whether reality had hidden depths was no longer a matter of preference, it had become a matter of evidence. Bell had drawn a boundary. On one side, hidden variable theories, local, deterministic, carrying their predetermined answers from the moment of interaction. On the other side, quantum mechanics, irreducibly probabilistic, with correlations stronger than any predetermined coordination could produce. The boundary was mathematical. What was needed now was an experiment precise enough to say which side of it nature lived on. The experiments came in stages. The first serious attempts were made in the early 1970s, using pairs of photons produced together and measured at separate detectors. The measurements were made quickly enough and far enough apart that no signal traveling at the speed of light could pass between the two detectors in the time available. Whatever happened at one detector could not have been influenced by what happened at the other. The conditions Bell required were met as closely as the technology of the time allowed. The results violated Bell's inequality. The correlations between the paired photons were stronger than any local hidden variable theory permitted. They matched the predictions of quantum mechanics. The particles were not carrying predetermined answers. The outcomes were not coordinated in advance the way the gloves in separate boxes are coordinated. Something else was happening, something the hidden variable picture had no room for. Over the following decades, the experiments were refined. Loopholes that skeptics identified, gaps in the experimental design that could in principle have allowed a local realistic explanation to survive, were closed one by one. The detector efficiency loophole, the locality loophole, the freedom of choice loophole. Each closure required more sophisticated apparatus, more careful timing, more stringent conditions, and each time the loophole closed, the result was the same. Bell's inequality violated. Quantum mechanics confirmed. Local hidden variables ruled out. In 2022, the Nobel Prize in Physics was awarded to the physicists whose experiments had done the most to close those loopholes and establish the result beyond reasonable doubt. The committee's citation was direct. The experiments had shown that nature does not conform to local realism. The correlations quantum mechanics predicts are real, and they cannot be explained by any theory in which particles carry definite hidden properties set at the moment of their creation. What this removes is not just a particular theory, it removes an entire category of explanation. Any theory that is both local, meaning no influence travels faster than light, and realistic, meaning physical properties exist independently of measurement, cannot reproduce what experiment shows. One of those two assumptions has to go. Either influences can travel faster than light, which creates problems so severe that almost no physicist accepts it, or physical properties do not exist independently of measurement. The particle does not have a definite position and momentum sitting beneath the wave function, waiting to be uncovered. The wave function is not a surface sitting on top of something deeper and more determined. It is as deep as it goes. And if that is true, if the wave function is complete, if there is no hidden layer of definite values beneath it, then the question of what the wave function actually is becomes unavoidable. Not what it predicts, not how to use it, but what it describes, whether it is a feature of the particle or a feature of our knowledge of the particle, whether those two things are even distinguishable at this scale. The experiments close the door on hidden variables, but closing that door opens something harder. If the wave function is complete, if there is no deeper layer of definite values beneath it, then the spread it describes is not a gap in our knowledge, it is a feature of the particle itself. And that forces a question that feels almost too strange to hold steady. What is the wave function actually describing? The temptation is to treat it as a probability distribution in the ordinary sense, a bookkeeping device, something that tracks the likelihood of different outcomes the way actuarial tables track the likelihood of different life expectancies. The table does not cause anything, it summarizes a population. Each individual life is fully real and fully determined. The statistics are in the description, not in the people. But the wave function is not that kind of probability distribution. The evidence against it is precise and has been confirmed in experiment after experiment for nearly a century. When a particle passes through two narrow gaps simultaneously, and it does, the interference pattern on the screen behind is proof. It is not that the particle went through one gap and we simply do not know which one. If it had gone through one gap, there would be no interference. The pattern on the screen would be two bands of intensity, one behind each gap. Instead, there are many bands, alternating, the unmistakable signature of two waves overlapping and combining. The particle interfered with itself. Both paths were physically real at the same time. This is what superposition means at the level of the wave function. The particle did not take one path or the other while we looked away. It occupied both paths in a way that had measurable physical consequences. The interference pattern is not a statistical artifact of many particles each taking different routes. Fire the particles one at a time, with long gaps between them so no two are in the apparatus simultaneously, and the interference pattern still builds up slowly on the screen dot by dot, over thousands of individual detections. Each particle interferes with itself. Each particle was genuinely spread across both paths while in flight. The wave function describes that spread not as our ignorance of which path was taken, but as the physical reality of the particle during transit. Both amplitudes were present. Both paths contributed. The wave function was not a summary of hidden information. It was the thing itself, the actual physical state of the particle, extended across space, interfering with itself, doing what waves do. And if the wave function is the thing itself, then the spread in position and momentum it encodes is not a gap waiting to be filled. It is not a placeholder for values that exist somewhere and will be found eventually. The values are not there to be found. What is there is the wave function. What the wave function describes is what is real. The particle before measurement is not a located thing with a hidden speed. It is a spread of amplitudes across space and frequency, and that spread is as complete a description of the particle as physics can give, not because physics is unfinished, but because the particle is not more definite than that. There is a word that gets used often when people describe the quantum state of a particle before measurement. Blurry. The particle is blurry, the thinking goes, like a photograph taken with an unsteady hand, where the subject was somewhere in that region but the image failed to capture it sharply. The blurriness is in the picture. The subject was always crisp. Find a better camera and the blur disappears. That picture is wrong in a way that matters. Blurriness implies a definite thing rendered imprecisely, a smeared image of something that exists sharply underneath the smear. Superposition is not that. The particle before measurement is not a crisp thing rendered poorly. It is a genuinely spread state, one in which multiple conditions are physically present simultaneously, each carrying its own amplitude, each contributing to what the particle does next. The spread is not in the rendering, it is in the particle. The double gap experiment makes this concrete in a way that the blurriness picture cannot survive. If the particle were simply a crisp thing whose location we had failed to capture precisely, if the blurriness were in our description rather than in the particle, then the particle would have gone through one gap or the other on each run. Its path would have been definite even if unknown, and a particle that went through one gap cannot interfere with itself. A definite path through a single opening produces a single band of intensity on the screen behind it. The pattern would be simple, additive, two overlapping blobs of probability, one from each gap. The pattern that appears is not that. It is an interference pattern, bands of intensity and shadow that can only be produced by two wavefronts overlapping and combining, reinforcing where their peaks align and cancelling where a peak meets a trough. That pattern is physical evidence that both paths were occupied simultaneously. Both amplitudes were real. The particle was not blurry, it was superposed. Those are not the same thing, and the difference is not subtle. Superposition means the particle carried both possibilities as active physical states, not as competing descriptions of an unknown definite reality. When measurement happens and one outcome emerges, it is not that the mystery resolves and the true location is finally revealed. Something more significant occurs. The spread of amplitudes, the genuine physical occupation of multiple states, gives way to a single outcome. And that transition, from spread to singular, from superposed to definite, is the most contested and least resolved part of quantum mechanics. It is called collapse. And what it actually is, what is physically happening when a superposed state becomes a definite one, is a question the theory describes with precision but does not fully explain. What the theory says is this: before measurement, the wave function evolves smoothly and continuously, spreading and interfering according to the wave equation. The moment a measurement occurs, the moment the particle interacts with something large enough and irreversible enough to count as a detector, a single outcome emerges. The interference vanishes. The spread resolves. One value is recorded and the others are gone. The question of where they went and whether they were ever fully real is what the next layer has to face. Something happens at the moment of measurement that the wave equation does not describe. The wave equation is precise and continuous. It governs how the wave function evolves through time, spreading and interfering and propagating in a way that is fully deterministic. Given the wave function at one moment, the equation tells you exactly what it will be at the next. No randomness, no ambiguity, no collapse. And yet, collapse happens. A particle that was genuinely spread across multiple positions, whose superposition was physically real, as the interference pattern proved, is found at one location when a detector registers it. The spread does not gradually narrow as the measurement approaches. It does not slowly concentrate around the outcome that will eventually be recorded. It persists, fully spread, until the interaction with the detector occurs. And then there is one outcome, The others are simply absent. This transition is not described by the wave equation. It is an addition to the formalism, a separate rule that says, when measurement occurs, the wave function updates discontinuously to reflect the outcome. The spread collapses to a spike. The superposition gives way to a definite value, and the probability of each possible outcome is given by the amplitude of the wave function at that value, squared. This rule works. Its predictions match experiment with a precision that has never been exceeded by any physical theory. But the rule is silent on what is actually happening physically when the collapse occurs. The silence is not a gap that further calculation can fill. It is a gap in the interpretation of the theory, in the account of what the mathematics corresponds to in physical reality. And different physicists have filled it differently, producing interpretations of quantum mechanics that agree on every prediction and disagree on everything about what those predictions mean. In the Copenhagen interpretation, the wave function is not a description of physical reality, but a tool for predicting measurement outcomes. The question of what the particle was doing before measurement is not a meaningful physical question. Reality, in this view, is defined by what measurement reveals, and asking what existed before the measurement is like asking what a piece of music sounds like when no one is listening. The question does not have an answer because it does not have a referent. In the many worlds interpretation, the wave function never collapses. It continues to evolve according to the wave equation without interruption. What looks like collapse from the inside, the emergence of a single definite outcome, is the result of the measuring device and the physicist operating it and the entire surrounding environment becoming entangled with the particle's superposition. Every outcome occurs. Each one becomes real in a branch of the wave function that no longer interferes with the others. The spread does not resolve. It proliferates. Both interpretations reproduce every experimental result quantum mechanics has ever predicted. Neither can be distinguished from the other by any measurement currently conceivable. The collapse, in one view, is real and instantaneous and physically unexplained. In the other, it is an illusion produced by entanglement, and what looks like a single outcome is one thread of a vastly larger superposition that continues without end. What actually happens when a measurement is made remains, after a century of the most precise physical theory ever constructed, an open question. The measurement has occurred. One outcome has emerged. The detector has registered a position, a momentum, a spin, some definite value pulled from the spread that the wave function described. And the natural question, the one that feels almost impossible not to ask, is what was there before that happened? What was the particle in the moments before the interaction that forced a definite outcome? The hidden variable experiments already closed one answer. The particle was not a definite thing with definite properties moving through space on a determined path, its true values concealed beneath the probabilistic surface of the wave function. That picture cannot survive what the Bell experiments showed. Local realism is gone. The particle before measurement was not secretly located somewhere specific, secretly moving at some exact speed, waiting for the measurement to reveal what was already true. But closing that answer does not automatically open another. What remains is not a clear picture of a different kind of reality. What remains is the wave function, a mathematical object that assigns amplitudes to possibilities, evolves continuously according to a deterministic equation, and gives way to a single definite outcome at the moment of measurement in a transition the theory describes but does not explain. The wave function before measurement is not a description of ignorance. The experiments confirmed that. But what it is a description of is a question the theory leaves genuinely open. One answer is that the wave function describes a real physical field, something that exists in space the way an electromagnetic field exists, something that has physical effects, something whose spread is a feature of the world rather than a feature of our knowledge. In this view, the particle before measurement is the wave function, not a particle riding inside the wave function, not a hidden point carried along by it, but the wave function itself, spread and interfering and physically real in every region where its amplitude is non-zero. The measurement does not reveal a pre-existing location. It creates one by forcing an interaction that the continuous spread cannot survive. Another answer is that the wave function describes something relational rather than absolute, not the state of the particle in isolation, but the state of the particle relative to a possible observer or a possible interaction. In this view, there is no single fact about what the particle is doing before measurement, because physical facts are not absolute. They are defined by interactions. The particle has no properties independent of the relationships that bring those properties into being. Reality, at this scale, is not a collection of objects with intrinsic states. It is a network of interactions, each one defining something that did not exist before the interaction occurred. Both of these answers are live positions held by serious physicists. Neither has been ruled out by experiment. Neither produces a prediction that differs from what quantum mechanics already predicts. They are not competing physical theories. They are competing accounts of what the physical theory is about, what its mathematics points to when you follow it all the way down and ask what is actually there. And sitting underneath both of them is the same irreducible strangeness. Before the measurement, the particle was not nothing. It had a wave function. The wave function was doing something, evolving, spreading, interfering with itself in ways that left marks on the world. But it was not doing that as a located object moving through space. It was doing it as something that does not fit cleanly into any picture built from classical intuition. Something that is real without being definite, present without being placed, physical without being a thing in the ordinary sense of the word. The uncertainty principle is described in most accounts as a limitation, a constraint on what can be known, a ceiling on the precision of measurement that nature imposes on anyone who tries to pin down a particle too exactly. And that description is not false, but it is incomplete in a way that leaves the deepest part of the principle untouched. The uncertainty principle does not primarily forbid knowledge, it forbids existence, not the existence of the particle. The particle exists, the wave function is real, something is there. What it forbids is the existence of certain states. States in which position and momentum are both simultaneously sharp are not states that are difficult to prepare, or difficult to measure, or difficult to confirm. They are states that the mathematics of waves does not contain. They are absent from the set of possible wave functions the way certain shapes are absent from geometry, not because no one has found them yet, but because the structure of the space they would have to inhabit makes them impossible. This distinction changes what the principle is saying about reality. A principle that forbids knowledge leaves open the possibility that the knowledge exists somewhere, in some form, in some layer of reality we have not reached. The particle might still have a definite position and a definite momentum. We simply cannot access both at once. The limitation is epistemic. It lives in the relationship between the observer and the observed, not in the observed itself. Hidden variables were exactly this kind of hope. The knowledge was there. We lack the theory to reach it, but a principle that forbids existence closes that door entirely. If the state of simultaneously sharp position and momentum does not exist, if it is not a real physical state that a particle can occupy, then there is no knowledge of that state to be had by any observer using any method within any theory. The limitation is not epistemic, it is ontological. It lives in the particle, not in the observer. And the Bell experiments confirmed that the ontological reading is the correct one. The knowledge was not hidden. The state was never there. What the principle actually forbids, then, is a particular picture of reality, the picture in which physical objects have definite intrinsic properties at all times, properties that exist independently of measurement, independently of interaction, independently of anything outside the object itself. Position and momentum in that picture are things the particle has. The uncertainty principle says they are not things the particle has. They are things the particle exhibits under the right conditions, under measurement, under interaction. They do not pre-exist the conditions that bring them into being. This is not a statement about human limitations. It is not a statement about the imperfection of instruments or the clumsiness of observation. It is a statement about the ontology of the physical world at its most fundamental scale. The properties we use to describe particles, the quantities we measure, the values we record, are not readouts of a pre-existing reality. They are outcomes of interactions between a quantum system and the physical conditions that force a definite result. Before those conditions are in place, the properties are not hidden, they are not waiting, they do not exist in definite form. And that brings the original question back into full view. The question that opened this was whether reality is inherently uncertain or whether we are measuring it wrong. It was phrased as a choice between two options. Neither one was selected. Something quieter happened instead. Both options turned out to be built on the same assumption, and that assumption is what the physics actually dismantles. The measuring it wrong option assumed there was a crisp, definite reality sitting beneath our observations, fully formed, fully located, fully determined, and that our instruments were too clumsy to read it without disturbing it. Better tools, more careful methods, a more complete theory. These would close the gap between what we measure and what is actually there. The uncertainty would dissolve. The particle would be revealed as the located, moving, definite thing we always assumed it was. We were the problem. Reality was fine. The inherently uncertain option assumed the same thing and then subtracted the resolution. Reality is definite underneath, the thinking goes, but nature has placed a fog over it that cannot be lifted. The uncertainty is permanent, but it is still a fog over something. There's still a fact of the matter about where the particle is and how fast it is moving. We simply cannot access it. The uncertainty is a ceiling on knowledge, not a feature of the thing being known. Both options preserve the particle as a definite object. One said we could eventually find its definite values. The other said we could not. But both agreed the values were there. The physics says they are not there. The particle before measurement is not a definite thing obscured by fog, temporary or permanent. It is a wave function, a real physical state that assigns amplitudes to possibilities, interferes with itself across space, and produces definite outcomes only when interaction forces one into being. The definiteness is not revealed by measurement, it is produced by it. Position and momentum are not properties the particle carries. They are properties the particle exhibits when the conditions for exhibiting them are physically in place. This leaves a picture of reality that has no clean name in ordinary language, because ordinary language was built for a world of located objects with intrinsic properties. At the quantum scale, that world does not exist. What exists instead is something that is real without being definite, physical without being located, present without being a thing in the sense we have always meant by that word. The wave function evolves, it spreads, it interferes, it responds to the geometry of its environment in ways that leave measurable marks on the world. And when something large and irreversible interacts with it, one outcome emerges from the spread, not because the outcome was always there waiting, but because the interaction created the conditions under which that outcome became real. Reality at its most fundamental level is not uncertain in the way a hidden answer is uncertain. It is not definite in the way a located object is definite. It is something the language of classical physics has no word for, a physical state that is genuinely open until interaction closes it, genuinely spread until measurement resolves it, genuinely without the properties we ask about, until the asking is itself a physical event that brings those properties into being. The uncertainty principle did not put a limit on what we can know about reality. It revealed what reality is. And what it is, at the scale where the principle operates, is not the solid located world of ordinary experience wearing a probabilistic disguise. It is something older and stranger than that, something that was always there beneath the classical surface, waiting for physics to look closely enough to see it.